All right, welcome to my webinar today. We're going to be talking about uh, how to make impedance measurements of ultrasonic transducer with the Digilent Analog Discovery. My name is Hussein Shakani. I'm representing my company, Ultrasonic Advisors, and I'm just really excited to bring this topic to you. And finding this device is really important, and it provided it's just it's so powerful. So I'm just excited to dig in. So I'm going to talk about the hardware, the analog discovery device itself, and any questions anyone has um, while I'm talking, please put that in the chat. It makes the presentation more interesting. Um, I'm also going to be going over the settings. So how to get accurate measurements and understand the accuracy of measurements is so important. No matter what kind of device you're using, if you're using a $50,000 Keysight impedance analyzer, or if you're using a $400 Digilent Analog Discovery, or using something even cheaper, or something you bought from, overseas and from like kind of whatever you use, you have to know how to evaluate the accuracy. And then I'm also going to be measuring the impedance response of an ultrasonic transducer, like an expert. Which I am claiming to be. But before we get into the topic in detail, let me just go over my company really fast. I have a consulting company called Ultrasonic Advisors, in which I help companies to develop ultrasonic transducers. Um, there are many different types of devices I work on. The services I provide are consulting, calls and meetings, transducer assembly, planning, electrical and mechanical analysis, and training, circuit development, finite element simulation, and also on-site consulting. I've worked with a whole different type of device, many different types of devices. A lot of my clients are bolt clamp Langevin transducers. Which are typically power ultrasonic transducers. Typically, my clients are people using ultrasonic transducers to send energy out. So it's more actuator based rather than sensor, but I do get many sensor device requests, and I've served those clients well too. So the great thing about my service is that I can help you utilize your own company's resources and kind of fill in the ultrasonic transducer expertise gap, whether if you need hands-on help or if you just need a kind of a consulting advisory partner. So the best way to get in touch is email. You can book a discovery call from my website, or you can also just stay on my email list. So let's get going with the topic. Um, so I'm going to first talk about the overview of the equipment and the software. Um, I'm going to talk a little bit about impedance theory as it relates to ultrasonic transducers. Um, we are going to look at the basic measurements. How do you just navigate just the very basic stuff on the with the analog discovery? I'm also going to talk about compensation. Originally, I wrote calibration. I'm not going to, there's no calibration I'm going to be showing, but there's compensation, and you'll be quite delighted with how accurate it is. And I'm going to show you, if you don't already know, how to take charge of your measurement accuracy, and be confident in it. So we're going to be checking the accuracy using resistors of known values. I'll be measuring a piezoelectric device, basically an ultrasonic cleaning transducer, and I'm going to be showing some tricks here, some different things that you may not have considered. I'm not just here to talk about the obvious, but I will talk about the obvious, but I will also go in depth to things you may not have understood, just from um, maybe a non-expert's starting use. I'll also talk about scripting, which makes the environment of the OEM software to measure impedance a bit more friendly for calculating parameters, because we have a specific type of thing we're trying to analyze with piezos, like resonant frequency, impedances, quality factors. So I'm going to be showing how to use some scripting, which is built into the program, which is really nice. And I'll be sharing that on my website when I release this video to the world. All right. Um, so first, I'll talk about the analog discovery device. Uh, it's set up like a general use device. It basically has, um, as you can see here, it has two scope kind of probes, which are semi-differential. It has power supplies, it has digital I/O, and it has two waveform generators. But basically, the important thing we're interested in and why it is used as a impedance analyzer is because it can measure two channels, voltage and current, and it can generate the waveform. Because if you can drive with the waveform of a known frequency, and we can measure voltage and current with two voltage channels, then we can measure impedance. So here's just some of the general stats, and you can go on their website and find that out. But the really nice thing about this specific device. I have the Analog Discovery 2, which is the model before, but this is the recent one, and you should expect similar results, if not better, with the newer one. But they have this attachment here, which makes it extremely useful, that you can plug this directly into the Analog Discovery there. As I show here, this is the Analog Discovery 2. After you plug that in, you're almost ready to go for your analysis. So there's not a custom board you have to build, which is really handy and very useful. The only thing I would suggest, and I'm going to make this kind of emphasize, that these connectors that come standard on the board are really quite terrible for sticking wires in and like pushing down these terminal. So I recommend removing that, and then once you remove it, it looks like this. Remove that, and then solder whatever connector you'd like to. Like here, I have a BNC. And then I made just a test probe here with a male BNC connector and some spring clips. And here are some of those products that I used to create that. And in general, we recommend to keep the leads short. Don't make your connector leads long, and just keep everything as small as you can in terms of length, in terms of parts. But here are just some of the parts that I used: the BNC connectors, the terminals, and these spring clips, which I cut in half. So if you cut one pair in half, then you get two. And as you probably know, most of the time when we do impedance measurements, almost all the time, 99.99% of the time, we're not applying a bias. So it doesn't matter what's positive and negative. It doesn't have any effect. I don't have anything here for shielding and grounding, but it's pretty accurate nonetheless. So and also the second nice thing, so firstly, they have an impedance attachment. Secondly, the OEM software does impedance measurement. So you don't need this impedance attachment. It basically puts a resistor to ground, like I've showed on many of my webinars. But you can buy that attachment for the resistor to ground. So there's the OEM software for the Digilent Analog Discovery is called Waveforms. That's the name. So I had to write in quotes because it's a very generic name. And there's a bunch of tools that this program has built in. The one you want is what we call impedance. So it's not anything new. It also has things like the scope and a bunch of other features and stuff. So we can do two things in the impedance mode. We can do both the impedance like frequency sweep, which would be, and I'm going to be showing this in a second here. Let me just fix this note writing pad here. So it'll have, and I guess I gotta change the color too, if I'm gonna be doing it there. You'll have the impedance, okay. You'll have the impedance and you'll have also phase here. And I'll be showing this a bit more explicitly with the actual data, not making up data. And you also have the LCR meter mode, which is the only limitation of this device. So it can measure your capacitance very well, but the problem is, and I'll get into in the very end, that it doesn't measure very small phase angles. And I'll show you what kind of problem that might cause, because typically in ultrasonic transducer analysis, we do measure capacitance at a lower than resonant frequency, and we want the phase angle to tell us, or we want the dielectric loss. So in order to, for example, I'm going to show this at the end, but in order to resolve a dielectric loss of 0.001, I think we have to be able to measure resolution of 89 point, I did the calculation here, is a 95, about 89.95. So we have to be measuring with a resolution of 0.05 degrees, and obviously to trust that, you have to probably have 0.001 at least. That's very small. So having the dedicated instrument like an LCR meter, to accent this, to be able to complete the whole measurement set, would be worth it, rather than buying like a $40,000 impedance analyzer just for that one purpose of getting that phase angle at low frequency. So if you combine this with the LCR meter running in the $400 range, you'll be able to complete the measurement set. Otherwise, you may struggle with high Q, low dielectric loss measurements. I haven't looked up. I'm sure there must be a way to get to initiate that, maybe some type of bridge measurement in order to measure small loss levels. But I don't know right now. If anyone does know, feel free to put it in the chat. I may cover that in a future video then, after kind of reviewing it and learning it myself. So for impedance measurement, you probably know what this is, that you're either here live or watching the video. But in DC analysis, we have voltage equals current times the resistance. For AC analysis, we have the voltage, amplitude, and phase equals the current, amplitude, and phase multiplied by a impedance value. Impedance is kind of like, and this is not a really proper introduction to impedance, but it's kind of, it'll allow for the conversion between voltage and current. It's kind of like resistance for AC. And it has both a magnitude and a phase. For a specific frequency. So how you would define impedance? So you would say at a specific frequency, like 10 kilohertz. This pen's a little bit too thick for me. Let's reduce that. Okay. So you'd say at 10 kilohertz, we have an impedance magnitude of, let's say, 500 ohms, and let's say negative 86 degrees phase. That is a proper definition of impedance. It's not just ohms, or it's not just phase angle, it's both, and that will tell you that current is lagging voltage by 86 degrees at this frequency, 10 kilohertz, and you divide voltage by 500 and you'll get the current amplitude. So there's phase angles, there's real and imaginary parts. And for the piezo resonator, we have our resonance and anti-resonance, and it is a simplified form. It is a Butterworth Van Dyke circuit with a capacitor in parallel with an LCR circuit, which causes both the resonance and anti-resonance phenomenon. So this branch is responsible for the resonance, which is low impedance. In the high impedance state, this basically inductor resonates with this capacitor in anti-resonance, such that current is blocked and impedance is maximum. At off resonance, we don't have influence from a resonance effect. So we basically just have these two capacitors in parallel, they just basically add. So the important parameters that we look to measure in ultrasonic transducers are typically capacitance, the dielectric loss at a off resonance frequency, the resonance frequency, the resonance impedance, the anti-resonance impedance, the anti-resonance frequency. We may look at admittance and series resistance. I've discussed that, I think, in other videos sometimes. So that is the impedance analysis review. Now, how does the analog discovery measure? So this is the circuit. Circuit for the analog discovery. So it applies a waveform using its generator, and it measures voltage channel 1 is hooked to ground and also above the device under test, and channel 2 is hooked over a resistor branch. Now, the nice thing about the analog discovery is that because it has analog inputs and outputs, you can select between different resistors on this board. If you notice that this board has these relays and it has these little resistors here, obviously they're not high power, but they can also you can switch between the resistors, which makes it handy. For if you want to measure a very low impedance, you can choose a lower resistance. You can choose 10 ohms, but if you want to measure a higher impedance, you can go all the way up to a mega ohm, but that's not really necessary or required. In this video specifically, I talk about 100 ohms and 1 kilo ohms for measurement across a very wide range. So you don't have to keep changing your values, which is a little bit of a fallacy, and I'll be evaluating that for the benefit of all those who watch. So the voltage that's of the device under test is voltage 1 minus voltage 2, and the current is equal to just voltage 2, being it the current times the resistance. So if you divide voltage 2 by the resistance value, you'll get the current, and therefore you have current and voltage, therefore you can calculate current magnitude. The impedance magnitude, and the phase is then calculated internally. So all this is done in the program, so you don't have to worry about it. I've read the documentation, so it uses a form of FFT to calculate and to measure voltage and current and calculate the phase difference. So that is good. It's not using zero crossing. I believe from the documentation I've read on their forums and everything, and I've seen actually from the evaluation of the measurement that I believe that. I believe that they're using a form of the Fourier transform method, and they are getting phase and impedance to be very accurate. And note that you don't have to use their board. You can use your own board or your own resistor circuit by putting a resistor. You just have to set it up, and there's a couple of ways that they have to set it up. I won't go over that, but I'm basically going to be using the adapter today. But note that you don't have to use the adapter. It's especially nice if you only have one type of device you're measuring, so you can have a kind of a stable measurement platform without too many settings. So, all right, we covered impedance theory, the circuit of the analog discovery, the basics of the analog discovery, basically what it is. So let's talk about basic measurement. So you navigate to impedance. So if you see my screen here, this is the waveforms program. So you navigate to impedance, and then it gets you to this screen. Nothing too fancy about that. Now I'm going to show you about compensation. I haven't seen calibration on here, but it's not really necessary if you already are pretty accurate. And I think the whole device itself is calibrated. And if you want to, you can apply transformations plus or minus 1% or something like that, some type of multiplication factors if you'd like to. But there's really no need to. And you can also define custom functions if that's your fancy to do, and there's probably other calibration methods there, but we're going to do compensation, which basically compensates for the fixturing for the cables with both open circuit and short circuit. So open circuit is primarily capacitance. The probe has capacitance. I think the whole system here I measured from the LCR circuit. My system has 55 picofarads of capacitance about, and there's also for short circuit it compensates for the inductance and the resistance of the leads. So by going into the program, and I'll just do it on the program, I guess it's a little bit more friendly there. So you could go into this button here, compensation, and you can compensate for each resistor value, or you can compensate for just the settings you already have loaded using this function here, perform open circuit or short circuit compensation. Note that you have certain settings that you compensate for, like you have to know your amplitude if you're doing averaging of measurements, and the length of time, the minimum length of time of a measurement too. So note that you have to set those settings in order to do the compensation, or it's not as valid as it could be. And you also make sure you enable by checking the check mark here in the little toolbar menu. So we have both LCR and impedance measurements that you can do. So without calibration, the LCR meter the LCR mode was showing 23 picofarads of capacitance. After calibration at 10 kilohertz, it was showing 0.5 picofarads. And just to note, sometimes it's not really necessary to do calibrate to do compensation um, when you are not measuring anything anything where that series capacitance would impact your measurement. So um, I so sometimes calibration can get tricky, or it's another step. So you should evaluate whether you need to do it for the particular device you're working on. Um, I'll mention that so devices that have a very high anti-resonance impedance, high coupling factor devices, those definitely you'll need to do open circuit calibration. But especially higher frequency devices, but lower frequency devices like 40 kilohertz, sometimes you may not need to do this step. But nonetheless, you don't lose anything by doing it. So hey, go ahead. Um, so, and I'll mention, yeah, it really affects the anti-resonance impedance and its frequency if you do not compensate, but that depends on your transducer. Here I do the short circuit. So with short circuit, without calibration, we get I'll just look at the impedance value. It's 120 milliohms of impedance, although the phase is 22 degrees. And here we after calibration, it's 7.5 milliohms and 0.02 degrees. I don't remember, and this is set at 100 ohms. So this is all done at 100 ohms of that resistor value. Note that you have to toggle whenever you want to when you load up the program the first time, you should toggle between two values to get it to actually switch, because it only initiates the switch whenever you change. So make sure you toggle back and forth because those relays are not really active unless you change. That's what I've noticed. Okay, so I showed you the compensation, and so checking the accuracy. So this is something that all folks in ultrasonic should know, and should look for measuring accuracy of their devices that they're using for measurement. The easiest and best way to do it, one of the best ways to do it is to use uh, um, accurate or precision resistors that are non-inductive. So metal film resistors, which are almost always blue in color, they're 1% and don't have negligible inductance. So because they're accurate, you can use them for testing the accuracy of your device. Your impedance measurements are very essential for doing anything custom, any custom device. Um, and I recommend just kind of a random thing to buy it in this binder. Otherwise, you have this whole pack of resistors, which is just pretty annoying to use, and it never ends up where you want it, and you can't find anything. And I've dealt with too many headaches, so don't buy the box of resistors with packets in it. Buy the binder, and this is what I also use. And this is nice, 1 ohm to 10 mega ohms. I'll be testing all those values in from one in the logarithmic form, I guess. So 1 ohm, 10 ohms, and so on. So this is my test setup. Well, I just have the analog discovery with the resistor at the end. Everything is calibrated. As you see here, I did the calibrations. So this is another nice thing about the program is you can put multiple plots on top of each other. So here I have 1 ohm, 10 ohm, 100 ohms, 1 kilo ohm, 10 kilo ohms here. And specifically showing for these lower ohms, these lower settings, they're very accurate. I don't think did I show any of them. Okay, so they're pretty accurate in the lower settings. Where I found there to be error starting for the 100 ohm setting was at 10 kilo ohms. But if you notice, we have 10 kilo ohms here, and where we start, and it's 5% is 10.5, right? So this is 5% plus or minus. So we do have a little bit of noise, you might say, or this is also sometimes bias from the calibration procedure that the signal is not very large for short circuit or for open circuit, so you're not really going to get a good you have error in that result just due to how small the signal is, but it doesn't get anywhere near to plus or minus 5%, even up to 100 kilohertz or up to 1 megahertz. It's not even 5% off. So one could say that we can measure 10 kilo ohms in this setting, all the way up to 1 megahertz at least. And this device goes up to 10 megahertz. I don't evaluate that high, but whatever settings are important for you, you should evaluate there. I'm just working in general settings. Here I want to show you other options that you have for improving the measurement. So you have averaging. So there's both time averaging here, like minimum of 10 milliseconds of data, and there's also a number of like samples taken. There's also the settling function, and I want to talk about this for one moment. The settle is very important for high Q resonators because they take a while to settle down once you drive at that frequency there. So in order to get stable results, you want to experiment with what settle values would be the best. Obviously, for a resistor, there's no settle value. It is what it is. But uh, uh, for a resonator, you will want to understand what the settle values are. Many of these parameters are also present on standard commercial impedance analyzers, um, but some of them are a little bit more unique to the setup here. I don't think there's any bandwidth kind of any bandwidth options, but I might be incorrect. But there is averaging, there is number of there's time for measurements. There's a lot of these, some of these options are present. And I just want to make sure I show them more. So without compensation, this is the green. Without open circuit compensation, you get the green, which is the impedance starts to drop, obviously, as the parallel capacitance of the probes start to really affect that high frequency. But we do compensation, so that's not a problem. In this plot here, I'm just trying to improve the results by changing different settings. I don't think I'm gonna be able to improve it very much. I'm not able to get better than like 2% here, as you can kind of see, but that's very good. I don't for in terms of repeatability. Here I look at 1 mega ohm. So we're doing 1 mega ohm measurement with a 100 ohm resistor. It's not very good. It's like 10% error, which is not terrible, but we probably, if we do have if you do have a device that has a near 1 mega ohm impedance, which does happen for thickness resonators, they will have a high coupling factor and a very high anti-resonance impedance. We do want to watch out for that. But in this case, it's not going to, you wouldn't want to use it for 1 mega ohm. And I'm just giving an example here. So for 100 kilo ohms, it seems to work well. So 100 ohms is very good for 100 kilo ohms. This is about at least to 100 kilohertz. It's not excellent, but it's not terrible either. So it can be used accurately. But I think the final takeaway from the settings that I did, and I'm going to be ending the settings part really soon here. I wanted to show this plot because this will be useful for you when you're testing the accuracy of your measurements. And so this plot here, I perform open circuit and short circuit measurements with and without compensation. So this top red line is open circuit with compensation on. This bottom line is short circuit with compensation on. And this, sorry, with compensation off. But when you turn on compensation, you get higher open circuit impedance and lower short circuit impedance. So if your measurement values, like if you're going to be measuring a device, let's say at 100 kilohertz, and you're going to be working in between, and your anti-resonance is 10 kilo ohms, and your resonance is around 10 ohms, you don't need to do any compensation for your particular device. So it's useful to see. It also can be useful to evaluate probes because you want to compensate at least as little as possible. So you'd like your probes to be low impedance. You don't want them to have like nanofarad or like hundreds of picofarad impedance. 50 is even pushing it, I guess, too. Um, so with that, this is 100 ohms is still not very good for 1 mega ohm, which I'm showing here. And basically what I'm going to get to here is one kilo ohm works very well. Basically, so this is the compensated 1 kilo ohm where we have I guess far into the megahertz range. It's still above 10 mega ohms out open circuit impedance, and under about 100 milliohms short circuit. So it's pretty good. So I recommend just using one. Let me just get to this part. 1 kilo ohms, and there's a couple of numbers here that can also be useful. But just this is what you would want to actually have. So you would want to know that I can measure a minimum of 10 ohms, let's say, and a maximum of 100 kilo ohms, and I don't have to change my resistor setting. I guess all of this is just showing, because later what you're going to find is it's handy that the program tells you if you're measuring if your resistor is too high or low. So it's handy, but it also will cause you to do multiple measurements and doubt your measurements. So making that process as simple as possible is important. And that's actually why I spent so long talking about evaluating the accuracy. So I recommend using the 1 kilo ohm setting, and you can measure low impedances and high impedances, um, probably for all power ultrasonic transducers that you'll likely ever encounter. Um, so um, let's talk about measuring the piezo impedance. Um, so here I have the piezo electric device hooked up in ultrasonic cleaning 40 kilohertz transducer. Um, and I also want to mention, especially for transducers that are mounted, they're they're low in anti-resonance impedance and they're high in resonance impedance. So they're very easy to measure. You don't have to pay much consideration at all for accuracy. But for unmounted high Q resonators, that's where things are important to pay attention. So I just ran a sweep from 1 kilohertz to 1 megahertz. But the step size is important to consider. So let's take a look at what I did here. So first of all, I changed the color, which you can do. You can right click the screen, you can change the color. It seems like it's more legitimate because it's more like a traditional instrument with a black background. Great, maybe your colleagues will say, good, this seems like it was before, because colors really make a difference for people trusting the data. So I had 1 kilohertz to 100 kilohertz sweep. Note that I went into the options and I changed the sweep from logarithmic to linear. And then I put the steps. You can increase the number of steps here to 10,000. But here I have 1,000. I'm using the adapter. Make sure you have this adapter selected, or then and this actually gives the circuit of the adapter already too. And I always use 2 volts. 5 volts seems like sometimes it might require too much current from the analog discovery, depending on the impedance of the device under test. So 2 volts is pretty stable all around, I found. So obviously here you have the impedance and you have the phase. The phase you can access by clicking this button, and you can move these windows around. It kind of becomes a bit annoying, but you can get it to work the way you want. And you can also save your workspace, as they call it. And I use this notes. I click notes and I hover it around, because then I start taking notes about what rare resonance frequencies were and everything. So here, I kind of I think I used this X tool, and I just kind of marked down every resonant frequency. Um, so that's one way of saving data, just by screenshots, which is why it's so nice to have all this on your computer, is because you can easily save the data. I'm sure many of us can many of us resonate with the experience of like looking at data on an impedance analyzer and not saving it almost ever. But this is so easy to save, especially with screenshots. Um, so this is a close-up view of the 40 kilohertz resonance, and these were that list of resonances that I had earlier. Um, I mean, so those data points. And if you see here, there's like this like error resistor too low. I don't believe you because I'm actually like right at 100 kilohertz, 100 kilo ohms. I'm way this the 1 kilo ohm resistor works until 1 mega ohm actually. I was looking at so we're way fine. Um, because this is a high Q, you might want to experiment with the settle. How long you allow the waveform generator to run before data is collected. So I start writing down the data here. There's an alternate way which is much faster. I'll describe that in a second. But in order to get the quality factor, which is an important aspect, or the admittance according to the maximum, or the resonance frequency according to the maximum parallel conductance, if you click admittance, which I'm showing it here, and you click a GP, which is parallel conductance, you'll get a peak, which is going to relate to your, as I like to say, real admittance, and that'll give you a peak only related to the LCR circuit. And if you go into the impedance section and you go click RS, then it'll give you the peak related to the anti-resonance only. And then you do the half, you look for the bandwidth of half the maximum value in order to calculate the quality factors. And I wrote all those numbers down here, like resonant frequency, parallel conductance, impedance, bandwidth. So the Q factor ended up being 796. I did the similar thing for anti-resonance, and I wrote down the frequency between resonance and anti-resonance. And that's pretty much what you need for that, for analyzing a transducer. I went back to the meter mode because we do want that 10 kilohertz resonance, 10 kilohertz, sorry, LCR values. So when I ran the Analog Discovery, this is what I got for the capacitance and the dielectric loss, 0.0015. However, the LCR meter gave me 0.00008. This difference can be significant if you assemble many transducers and you get this difference in values. So it's important to be able to track. And here you see like the phase is negative 89.91. So it's the requirement to be able to measure very accurate phase values is too high for this specific device in terms of accuracy and noise level. The type of circuit is being used is not the circuit to measure very accurate phase, but it's like many times over good enough or very good for resonance, anti-resonance impedances, or even capacitance in general, but not very accurate for phase. However, if you have like a low Q, like a transducer, like a PZT5, or if you're measuring something that's already mounted in a device, this will still work. So you can still measure those phase angles pretty well. So the last thing I want to talk about is scripting. So there is a lot of useful functions of this waveform software. One of them is its ability to put in scripts directly into the program instead of having to like somehow fumble around with using some external programming language that's not native inside of the program. So if you go to the main menu and you go to script, which is right here in this blue, I'll just add something here. There you go. If you go to script, you'll get to this menu, and I have actually code that if you put in and you press after running an impedance sweep, if you just press play on this code, it'll spit out all the values. So it'll spit out the Q factor, it'll spit out all the resonance values that you want, and you can look at the code. It's like JavaScript. They don't have all. It's not very well documented, but I was able to figure out a lot of it. And with this functionality, it becomes extremely palatable and very useful for ultrasonic analysis. So I'll be posting a link to this code whenever I post this video online, and it's going to be linked in my website, probably in the resource section. So here are the takeaways. So the Digilent Analog Discovery, which is about $400, is a very appropriate tool for ultrasonic transducer analysis. It has an easy to use impedance analyzer attachment, but that attachment is not necessary. You can use your own circuit along with that to attach to the system, either from either from the just like jumper cables, or you design and make your own board. So I would recommend replacing the OEM connector with BNCs or another type of connecting cable, because a lot of times it doesn't connect properly, and that reduces the usability and the accuracy of the device if you have to worry about those connections. The 1 kilo ohm setting is very accurate. I would trust it from 100 milliohms to 1 mega ohm, up to 1 kilohertz and beyond, 100 kilohertz and beyond, which when that's most of my work is under 100 kilohertz. But just investigate the settings for your application. And how do you investigate that? You just use the resistors to see, well, I have a device at, let's say, 5 ohms at 1 megahertz. Is it going? Can I trust it? And what you do is you measure those 10 ohms with your system, and you try to see how accurate you can get, and what the open and short circuit impedance values are. I would recommend using scripting for easy data analysis. The weakness of this device is that the phase measurement is not accurate, and for RF, like very high frequency, like I haven't used this very much above 1 megahertz or so. So I've used it for 2 megahertz. Those were not high Q transducers, so it wasn't hard to get accurate. But when you're looking at higher frequency, typically you are at a loss unless you choose kind of the expensive equipment. It's hard to get around it at that point. Yes, because if you're measuring a dielectric loss of 0.001, the phase angle between voltage and current is negative 89.95. So in order to get resolution there, you have to be able to measure another degrees, which is like which I was never able to get that to happen on my own personal work that I did during PhD. So I had to give up part of my PhD work because I couldn't get more accurate measurements than that on high Q devices. But I did finish, as you know. But yeah, just the warning there. Don't really take those dielectric loss values too seriously, especially for high Q. For low Q, take them seriously. For high Q, don't take them that seriously, unless you're using an LCR meter, which I do recommend having one, and it is something that I have purchased for the work I do. I do have a dedicated LCR meter, which can measure lower phase angles accurately, and I use both, and that ends up working out very perfectly. All right. So with that, I will end the presentation, and I'll just end it on this screen, and I will, I'll stop my share. Stop the video.